Today we're going to look at our second to last topic of the unit. It's all within this energy framework. Specifically, though, today we're going to talk about work. We define work as, quite simply, as the change in energy experienced by the object, and the energy gained or the energy lost by the object. Now, let me ask you this. What do you need to do to change the energy of this desk that's sitting right here at the front of the room right now? Right now, its energy is 0, right? What do you got to do to change its energy? In other words, to give it energy that it doesn't have right now. This is not a crazy hard question, right? Don't make it harder than it has to be. What do I have to do to this desk to change its energy? In other words, to add energy to it. Apply a force, right? You got to push it. A push or a pull. If I push on this desk, then I might change the desk's energy. But watch this. Okay, right now I push on this desk. Am I changing the desk's energy right now? The desk has 0 energy right now. What does it have after I push it? 0. Haven't done any work on the desk, right? So you're absolutely right, Parker. I need a force, but that's not all that I need. What else do I need besides a force? I need force on this desk, and I need movement of the desk. I need a displacement of the desk. It's not enough to just apply a force on it. You have to apply a force and cause movement. Okay, you can apply all the force you want. If it doesn't change the speed of the desk, you haven't changed the energy of a desk. So we're going to say work depends upon those two things: the force acting on the object and the displacement of the object. Now, we got to be careful with this force and displacement. Okay, we said that it's sufficient to have a force and a displacement. Yes, it is, but remember that I can push on this desk in any one of a number of different directions, 360 different directions, right? At all kinds of different angles. What's important to note here is that only the part of the force that causes the displacement matters. So in other words, if I take this desk and I push down on it like this, and this desk moves like this, not all of the force that I applied causes the motion. Right? We need, in order to cause a gain or loss of energy, I need a force and displacement. But it's not just any force. It's the force that causes the displacement. Does that make sense? So if I push on it like this, yeah, I cause the desk to move, but some of that force isn't doing any work on the desk because it's only part of that force that's causing the motion. Now, if I said this was an angle of, let's say, 30 degrees, how do you think you'd find the part of the force that causes the motion? Yeah? Yeah, you'd have to find the x value of it, right? Which we would say, okay, if you break this down into an x and a y component here, you would say that cosine 30 degrees is equal to opposite, that's the x component, over the hypotenuse, right? In other words, the force that we want to use, and that is the x component, is equal to the force times cosine theta. So what we do in this case is ultimately multiply the x component of the force by the displacement. Remember, force and displacement are necessary, specifically the force that causes the movement, which is the x component of the force. Let's write down an equation here. In general, we'd say that work, by the way, work is equal to, fundamentally, the change in energy. And this part of the equation is called the work-energy theorem. The work, or the change in energy, is equal to F times D. But only the part of the force that causes the movement, which is the parallel part of the force, which is the x component of the force. Nice thing about this equation you usually see it, and including on your data sheet, with the x component found for you. Instead of saying f times d, we often write it as f times d times cosine theta, which says to us, like let's say this value of the force was 100 newtons, and the movement was 20 meters. Well, you go look at it and say, well, we need to find the x component of that 100 newtons and multiply by 20, but we can look at the equation and say the equation does that for me. F times d times cos theta finds the x component of the force for me. Now, let's say the desk moves. I push the desk. Let me draw it here. Here's the desk. I push it this way. It moves this way. What's the angle between the force and the displacement? 0. Everybody in your calculators do this right now. Everybody on your calculator do this right now. Go cosine 0. What do you get? What do you get? 1. So in other words, if the force is in the same direction as the displacement, then all of the force is causing the displacement. Cosine 0 degrees is equal to 1. The equation becomes f times d. We don't even need the cos theta then, right? How about this one? Let's say that I push on this desk straight downward, like this. So here's the desk. I push downward on it. But let's say for whatever reason, it's moving this way. Maybe like it had already been given a push, maybe it had been bumped by something, whatever. It's moving already and I push downward on it. Like, does that force that I apply cause movement? No. So am I doing any work on this desk? No, there's force and there's movement, but the force isn't causing the movement, so I'm not doing any work on it, right? I'm not changing the energy of this desk. I haven't done any work on it. What would the angle between the force and the displacement be? 90 degrees. What's cosine 90? On the calculators right now. Cosine 90 is 0. So the equation becomes f times d times 0, which means the work done is 0. Do you see that? I'll tell you what, most times you get a question involving work, you can leave off the cosine theta because theta is equal to 0. If it's not, then make sure you include it. But remember that they're doing you a favor by giving you that form of the equation. We need the x component of the force. We need how much of the force causes the motion. But the cosine theta does that for me. Does that make sense? So if you push it one way and it moves that same way, just drop the cos theta if you want. If you push it one way and it moves in a different direction, then you need to include the theta and say f times d times cosine theta. All right? Okay, let me give you a couple little, not numerical examples of this, but just a couple examples of when we have to include an angle, when we don't. Okay, let's say we got one of those wagon problems, but we're analyzing it differently. We're analyzing it as an energy problem. Okay, so I pull it this way and it moves this way. What do I use, f times d, or do I use f times d times cosine theta? Do I need to use an angle here? Do I? Yeah, what would it be? What would theta be? What is it? 30 degrees, right. 30 degrees. What if, here's one for you. What if it's moving this way, and I apply a force this way. I lift up on it. Do I need to include theta then? Technically, yes. What is theta? No, not 0. No. What is it? It moves to the right. I push on it upwards. Which way is, what's the angle between the force and the displacement? 90. But what's cosine 90? 0. What's the work done on this? 0, right? What about this one? What if I have something like this? Okay, I pull it up there, and of course, as I pull it up the inclined plane, it moves up the inclined plane. What angle do I use now? 30, right? Who says 30? Who agrees? Anybody say anything different? What's the answer here? Oh. The answer is 0. Why is the angle 0? Because what? I'm pulling it, yeah. Ben? Yes. I'm pulling it at 30 degrees, and it moves at 30 degrees. I pull it at 30, and it moves at 30. The angle there, F times D times cosine theta, that angle theta is not just any angle that's given to you in a problem. It's the angle between the way that it's pushed and the way that it moves. And that angle here is 0. It's pushed at 30 degrees. It moves at 30 degrees. The angle between the two is 0. Does that make sense? What if I did this? What angle would I use now in my F times D times cosine theta equation? It's moving parallel to the hill, right? I pull it up the hill, it moves up the hill. What angle do I use? Demi, do you have an answer there? No? Okay, I thought you were raising your hand there. Josh? No. Ben, is your hand up there? No. Josh? 20. Yeah, good. Why would it be 20? I pull it at 50, and it moves at 30. What's the angle between the way that I pull it and the way that it moves? 20. So it would be F times D times cosine 20. Does that make sense? Listen, guys, most of the questions you're going to see the angle is 0. If it's not 0, then make sure you just put it in, right? If it's 0, F times D. If it's not 0, then just put it in. Doesn't really make it any harder. You just got to use your calculator with some trig. That's all. It's an easy trig because you're already given the trig function. Okay, let's have a look at an example here. So what do we got here? 20 kilogram object gains 300 joules of kinetic energy. What is this question telling me here? This object gains this much kinetic energy. What do I have given to me? Clearly the mass is 20 kilograms, right? What is this 300 joules? What do I call that? Yeah, I could call that delta E, the gain in energy, but what's the gain in energy equal to? The work energy theorem says that work is equal to the gain or the loss of energy, the change in energy. So I could say that 300 joules is equal to W. Now let's push the difference of a distance, I should say, displacement of 100 meters. We want to calculate the force used to push the object. Now, when I say that, calculate the force used to push the object, like I may push harder if I push inefficiently. The force that's necessary to cause this is the force that's parallel, right? If I push it at another angle, I got to push harder. But best case scenario, how hard do I have to push? The force that's parallel. In other words, where the angle is 0. If the angle is 0, what version of the equation should I use? FD, why don't I just leave it there? I mean, if I say cosine 0, what's cosine 0? 1. So F times D times 1 is just F times D. My angle is 0. and then just make it F times D. Let's solve for force here. Force is work over displacement. By the way, work is a scalar. Force is a vector. Displacement is a vector. Force and displacement go together. Two vectors combined together give you a scalar for work. What units would work be measured in? Joules. It's energy. It's change in energy, right? Of course it's joules. Work is 300 joules divided by the displacement of 100 meters. What's my force here? 3.00 newtons. So maybe I pushed not with 3. Maybe I pushed with 4 at an angle. That wasn't the question. The question didn't say how hard did I push. The question said, what's the force used to push the object? What's the force that causes this motion? The force that causes this motion is the parallel component, where theta is equal to 0. So maybe I pushed with 4 newtons, whatever. Okay, but the answer to the question of how much force caused the motion is 3 newtons, because the angle was 0 degrees there. I would like you now to take a look at your energy worksheet number 3 in the booklet that was handed out to you last week. Specifically, questions 1, 2, and 3. Questions 1, 2, and 3 on energy worksheet number 3, please. All right, if you guys are okay with worksheet number 3, let's do another example. This one's also not in your book. This one says a 1,200 kilogram car accelerates from rest to 90 kilometers per hour. I'm going to circle that in red, draw attention to it, so I don't forget to convert that to meters per second. Over a distance of 200 meters, how much work is done? What's the net force required to do this? Let's write down some givens. We got a mass here of 1,200 kilograms. What else we got? Tell me something else, quick. Yep. VI is 0. Okay, what else? VF is 90 kilometers per hour. We're going to convert that to meters per second here now. By multiplying it by 1,000, dividing by 3,600, it gives me, I believe it's 25 meters per second. Is that right? The displacement or the distance is 200 meters. And I want to find the work done, and I want to find the force required to do that. Any ideas? Well, we'd love to say for work, W is equal to F times D, right? That's a valid equation. Sure it is. But what's the problem with that to find work? I don't know what F is. I don't know what F is. So I can't do that. What does work also equal to? What is work also equal to besides F times D? Change in energy. That's the work energy theorem, right? Okay, work is equal to delta E. Okay, let's try this. What's the final energy of this car? What kind of energy is it? Kinetic energy. So let's say the final energy is kinetic. What's the initial energy of this car as it sits there if we don't pay any attention to the potential there? To the chemical potential. 0. So let's say for the work, let's say 1/2 mv F squared minus 0, which is 1/2 of 1,200 times 25 squared minus 0. We can find work in 2 ways. We can multiply F times D, or stick a theta in there when necessary, F times D times cosine theta, or we can say it's final energy minus initial energy, the work energy theorem, change in energy. We do that for this one, we get 375,000, 3.75 times 10 to the 5 joules, which we're actually going to round to how many digits? 4 digits, 3 digits. This one is 2 digits. Final answer should be 2 digits, 3.8, yes. 3.8 times 10 to the 5 joules. Why was it good to write down the unrounded number, though, the 375? In case I need that for the next part of the question, which is what's the force, right? Okay, how am I going to find the force now? Don't make this one harder than it has to be. What's that, Patrick? Yeah, assuming that you push it in the same way that it moves, work is equal to F times D. F is equal to W over D. Yes, that is displacement technically rather than distance, but works there. 3.75 times 10 to the 5 joules divided by the displacement of 200 meters. And we end up getting 1.9 times 10 to the 3. Now, you understand that that wasn't the only way to solve that question. Right? That wasn't the only way to solve that question. You don't have to write what I'm about to write down in red if you don't want to. I'm just going to show you another way we could have tackled this. We could have said, well, VF squared is equal to VI squared plus 2AD. Solve for A, which is VF squared minus VI squared over 2 times D. And then once we got A, we could have solved for force using M times A, right? Does that make sense? And then, if we wanted to, we could have multiplied F times D, that force that we just got, and got work. So we could have done this completely backwards. But I would suggest to you the method that we used first with just work and work energy theorem, a little bit more efficient in this case. But there's often more than one way to tackle this, often more than one way. Okay. Try using work energy theorem right now just to kind of get the hang of it. And then on test day, I don't really care. Okay, whatever works best for you. Tackle it that way. Okay, let's take a look now at that worksheet number 3. This time, we're going to look at questions 4 and 5 on worksheet number 3. Okay, let's have a quick peek at number 4. It says a 1,300 kilogram car begins at rest and accelerates to 60 kilometers per hour. I'm going to circle that because I want to draw attention to it over a distance of 200 meters. How much work is done on the car? We know that work is equal to delta E. It's also equal to F times D. I don't know what F is. I know what D is. So I got a couple of options here. Patrick? I can find F using M times A. I can find A using VF squared is equal to VI squared, but that's not the best way to do this. The best way to do this is to say, well, work is equal to change in energy. They're both correct. The change in energy is final minus initial, and since this car is accelerating from rest, we're going to say its final energy is kinetic and its initial energy is 0. So it's just simply 1/2 of 1,300 kilograms times, what is that speed in meters per second? 60 times 1,000 divided by 3,600? 16.666. Use your unrounded number, 4 or 5 decimal places, 16.6667. Square that, and when we do that, I think we get 1.81 times 10 to the 5. And of course, since it's work, change in energy, the units are joules.